Good. How are you?
For the homework, can we turn into files?
Yep.
I have a Word, and then I have the problem number 2 with all the math work
Yeah.
on a PDF, but it won't let me insert it in the Word document and then turn it into PDF.
Yeah. You can do multiple files. That's fine.
Cool.
Yep. Hey, Jacob.
I was hoping you'd be here.
Mhm.
Let me step by step down real quick.
Okay.
So I added a wind force to that bridge like I was originally going to.
Yep.
And it was in megapascals, the pressure.
Okay.
And so I thought that that was just a little high for a wind force.
Mhm.
Because from what I was Googling, even like 70-mile-per-hour winds only produce forces in like the kilopascals or something, or like 12 point. Well, it was really pounds per square foot, but it was like 12.5. So I converted it, and it was something like, I don't know, something kilopascals.
Yeah.
But so I just put, I put 0.05
Okay.
megapascals, but again, I'm getting all my stress right here again. And I think it's because, I don't know if it's black. Oh, it's because my mesh is super tiny now.
Is that on the side of the fixed support? Or is that the displacement support?
That is, let's see, displacement, no, fixed.
Okay. Yeah, that makes sense because that actually in reality, this bridge in this default configuration is very under constraint, or not under constraint, but there's just barely enough constraints to make it so that it doesn't just fly away. And so because that you only have just one fixed support there, I think just the stressors are just going to concentrate on the 2 constraints, kind of no matter what we do. You'll probably see a more realistic stress distribution once you get to, I forget what number it is, but the second to last problem where I have you add some more fixed supports kind of on the bridge.
That's what I was gonna ask. How do I make this go away? How do I make the mesh go away again?
Oh, the mesh,
The
it's under
display,
view.
right?
So it's under view
Oh,
or
where's the view?
display. what a result.
Yeah, so this is what it looks like, and it's like, I was surprised, I was actually really surprised because on the other ones we did. So I was going up a little more slowly, right?
Mhm.
And then this is just my last one where it just like barely changed. Now I have a lot more. I have like 30,000 here, I think.
Mhm.
But like it started at the lowest mesh. It started, and this was only like 94 or something.
Mm. Oh, yeah.
And then it jumped up to hundreds. And then I was like, okay, let me take a few more millimeters off. And then it jumped all the way up here to the 600s.
Oh, yeah, you're gonna see that. So for mine, when I did the when you don't have enough mesh density, the stress gets really underestimated. Then kind of once you reach a certain point, then it kind of just shoots up like crazy.
Okay.
Yeah. So that's normal.
And then I thought this made a lot of sense here.
This
Which is
deformation.
like, yeah, because
Yeah.
you only have one reinforcing support here, so it's like these are just gonna want to buckle
Right.
because they're at the midpoint right
Yep.
here by this.
Mhm.
And then I guess it kind of made sense why it was like, but okay, but here, so then I'm getting my max strain here. But why am I not getting a high strain value here? If it's deforming the most, wouldn't the quotient of the original length over the, or new length over original or whatever it is, wouldn't it be the highest here?
I think it's just rotating. So I think it's just it's doing the same thing as the chair. So the
Oh,
chair is
okay.
just rotating, but it's
But
not
it's not
actually,
actually stretching.
it's
it
not
that
actually
much?
stretching. Yeah, so I think all the stretching is happening at the support.
Okay,
Because these parts are so far from the support that they're just kind of just going like that.
okay. I figured maybe this bridge was like really weak under shear or something since it wasn't getting any supporting.
Mm.
And then this was gonna cause a large shear force here, because like if it bends over and it pushes the support bar this way, and then that's gonna make that go like that.
Yeah.
Maybe it's putting a large shear force here at the
Yeah.
support.
No, that makes sense to me too.
Okay,
It's probably both things at the same time.
yeah, and that was it right there. So I'm assuming it's like it was before these supers, like that little bit in the corner too.
Yeah.
Probably just.
It is a weird loading configure. It is a weird constraint. We have just, and the other thing is we're constraining it at an edge where normally you want to constrain it on a whole surface of this. So I think that's also adding some.
Okay,
Some
so
stuff to it.
normally the whole road would be fixed?
Not the whole road, but you'll see later on. I'm having you fix it at each of the ends.
Oh,
the
each of them
seams.
was.
Yeah. That's more realistic.
As if there was a column underneath
Exactly.
it? Okay,
You'll see a much better result from.
okay, cool. All right, so I guess this is.
Mm.
Thank you, Professor.
Yep. Okay, it's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everybody. I'm back in the classroom. Okay. My fiance is doing a lot better. She was coughing really bad last week, but we got her tested for COVID twice. She was negative twice, so I'm safe to come back here. So it's good to be back. All right, and so the plan for today. Oh, we got a cold over the weekend. Oh, man, hope you feel better. The plan for today is we're going to continue our lecture notes with lower extremity biomechanics. So I'm hoping we can finish today, just so that we can kind of stay relatively on schedule. We are running a little bit behind from my original plan. That's okay, but I don't want to fall too far behind. Okay. Besides that, homework 4 is due this Wednesday, so it is quite a long homework assignment, and so I got some questions over the weekend, but if you ever run into any issues, definitely let me know. So. A big part of it, as you can see from the last lecture notes on upper extremity, a lot of it is statics. And so I think a lot of the questions I've been getting is just kind of dusting off the statics knowledge, dusting off the trigonometry knowledge. So, if you're struggling with that, don't feel like, no question is too silly for anything. So, it's better to ask, I've always lived by this saying that it's always better to ask and feel silly for a second rather than to never ask and feel silly forever. So, even if it's just a simple trig thing, it may seem like it's simple, but even when I was writing these problems, I struggled a lot with the trig too. So please don't be afraid to ask. Okay?
Yeah, the equations are like really long to solve.
It is,
I
yeah.
had a calculator, had to like do the parts, numerator itself, and
Uh-huh.
denominator parts, so I couldn't add it all.
Yeah, it's there's quite, it's a lot of arithmetic, a lot of algebra, and a lot of just tricks. So yeah, the volume, kind of the volume of the calculation you have to do is kind of insane. All right, question. So do you think I can go over a little today just to see different angles? Sure. Yeah, yeah. So I think the tricky thing that I kind of see consistently is that when I give you the attachment angle for the muscles, that's always relative to the limb itself, and so that's not relative to the horizontal. And so I think a good example of this is actually the first part of the second problem, 2A, where we have kind of an elbow that's kind of down like this, right? And so you have a muscle force that's kind of pointed upwards like this. And so that was theta M. And then we have the regular theta, which is the theta for the arm itself, is down here, okay? And so what I've been seeing is that a lot of people have been getting the muscle force for this one correct because it's basically you sum the moments, okay? But when people are going to sum the force in the X direction, sum the forces in the Y, I think there's a little bit of confusion on what to do with this muscle force here, right? Because the sum force, and let's just do the X direction just so you can see, right? And so we have, let's say, JX and JY right here, okay? And so the X direction, we can see that we have a JX, right? And so that's just purely in the horizontal direction. And then we have some term that involves FM, right? And so we have a minus FM here, okay? And just because it's the X component, we know that we're going to do a cosine. Let me actually move it to the second line. So it's minus FM cosine, okay? But what to put for the angle here can be a little bit confusing, okay? Because remember, this theta M right here, this is not measured relative to the horizontal. This is measured relative to the arm itself, right? And so you can kind of draw a line that's like that, okay? And so if it'll help you, because this entire arm is just one whole rigid body, what you can do is you can basically move, just for visualization purposes, you can move this force vector down here, right? Okay. And so you have an FM right there, and a theta M is just like that. Okay. All right, and so from here you can see that we have two angles here, right? And so we have the angle that the arm itself makes with the horizontal, which is theta, and then the angle that the muscle force acts with respect to the arm is theta M, right? And so the total angle, if we were to sum up these two angles together like this, right? It's just gonna be theta plus theta M, right? Because remember, we're summing up these forces, with respect to the X direction, right? And so the X direction here, this is with respect to the horizontal, right? And so any trigonometry terms that you put in there, any sines and cosines, should be with respect to that horizontal line, okay? And then same thing for the vertical too. So for the vertical, let's see, we have JY, and we have plus FM, and this time we're going to have sine theta plus theta M, okay? And I think we have an extra term in there for the weight as well, okay? Right? And so when you're doing your sum of forces, really think about the angles that I give you, and look at the figures that I provided you, and see what are the two lines of action that form these angles, right? So you should ask yourself whether the angle is with respect to the vertical or the horizontal, or if the angle that I'm giving you is with respect to a limb, okay? And if it's with respect to a limb, you can either add the angles or subtract them depending on their magnitude. And I think we're going to do another example today with the knee, where it's the same thing where we add them together, okay? All right, question. So for number 3, where the guy is doing an overhead press, can we move the FM to the joint and just do 90 minus 25? Yeah, sure. And so, you can do this trick where you move the force vector around, because we're basically treating these as rigid bodies. And so when you're doing a force balance, you can't do this with the moment balance. And so for the moment balance, you have to keep the forces in their proper locations because you have to compute the moment arm. But for the force summation, you can move the force vectors around, and it's still going to be the same thing because we assume basically the entire structure is a rigid body. And so I think for the shoulder press one, you're going to do an angle subtraction, because I think let's see, and I don't have it in front of me, unfortunately, but I think I think it's defined like this, right? And so I think the shoulder, I think the upper arm is like this, and I give you this angle is theta, right? And then I gave you the muscle force, which looked like this, right? And so when you put these two on top of each other, you can see that theta is going to want to rotate the whole whatever arrow that you're doing counterclockwise, whereas theta m is rotating clockwise here, right? Or they're rotating in opposite directions basically. And so if when you're doing this force balance here, let's say the force in the x direction, you can do Fm cosine, you do theta minus theta m. Yeah, because they're in opposite direction. I don't have it in front of me, but but I think it's something similar to this. Yeah, that makes sense because the person's overhead and the deltoid muscle is acting this way. So yeah, and so in this one you would do subtraction for the angles. Yeah. Okay. Any other questions on the homework? Okay. All right, so let's go ahead and pick up where we left off on last Wednesday then. And so last Wednesday, we were talking about lower extremity biomechanics. Okay. And in particular, we are doing static analysis of the lower extremity. Okay. And so I think we were doing this, we were in the middle of an example where we were considering someone that's walking with a cane. Okay. And so as a result, because remember we talked about last time, when you're walking, there's a very brief instant from when you walk where basically your foot is lined up with the midline of your body, right? Because basically that one foot, when your other foot's off the ground, has to basically support your whole weight. And so just to stay balanced, your foot has to be right underneath, okay? And excuse me. And that puts a lot of strain on your hip flexors, right? Because you can kind of try it yourself right now. So if you kind of put your foot towards the middle of your body, your hip kind of bends like kind of towards the middle of this. And so your hip flexor muscles, which are, let's say if this is that's your thigh, that's your lower leg, and that's your foot, okay? Remember, your hip flexor muscles are basically these muscles right here, right? And so let's say that basically the person's pelvis is like right here, okay, and their other foot is off the ground, okay. Right. And so your hip flexor muscles have to do a lot of work in this case because your legs are kind of bending, your entire leg is kind of bending inwards. Okay? When you're walking with the cane, the cane kind of shifts your center of gravity outwards. And so what that does is that it kind of straightens this leg out. And so you no longer have that, it's no longer kind of twisted so far inwards. It's a lot more straight. Okay. Right. And so the whole idea with this is to, for someone with an injured hip, then they can use a cane when they walk to help alleviate some of the pressure on their hip flexors. Okay. And we are doing a static analysis of this situation. All right, so let me go ahead and draw the leg. And so I'm going to assume the entire leg is just one rigid kind of pole right here. Okay. So there's our leg. And so right down here is the foot. And so this is where the foot's contacting the ground. Okay. And so at the foot, we're going to have an upward force being applied of 200 newtons. Okay. And that represents basically the weight of a person that's being placed on that foot. It's not the full weight because remember there's a cane that's off to the side that's kind of out of the picture. That's partially supporting the weight as well. And so I think we said the cane is supporting about a third of the person's weight. Okay. And so this is just basically whatever's left after that. Okay. All right. Let's see. And so what we said was the hip joint is maybe somewhere over here. So this right here is the hip joint. Right, so this is where the head of your femur, the head of your thigh bone is attaching into your pelvis, okay? And this is the joint at which we're going to perform our analysis. All right. And so let me just go ahead and draw a vertical line right here. Okay. Because we're going to draw some, put in some weights in here. All right. And so first thing we're going to need to know this horizontal distance. Because just like we've always done with these static analysis problems, we're going to be summing up the moments around the joint. And so we need to find out, what the lever arm is for this weight force, okay? And so we'll call this LF, okay? And I think LF has a value of 5 centimeters. Okay. That's relatively small because remember our foot is relatively straight up right now, okay? Next thing we're going to account for is the weight of the leg itself. And so we're going to put that right here. Okay, so this is the weight of the leg and it's going vertically downwards. Okay. We also need to know this horizontal distance between the leg and the hip joint. Okay. And so let's say the weight of the leg, we'll say this is 50 newtons, okay? And then the moment arm, we'll call that LL. Okay. LL here is going to be 6.5 centimeters. Okay. And the last force that we have here is going to be the muscle force for the hip flexor, okay? And we'll call that FM, and that's what we're going to solve for. Okay. And the distance between the horizontal distance between the muscle force and the hip joint, we'll call that LM. And we'll say that LM right here is 7 centimeters. We're also going to need to know the vertical distance here, okay? And so this vertical distance HM we'll say is 1 centimeter. And we of course need to know theta M. And so theta M here we're going to say is 70 degrees. But I define this muscle attachment angle a little bit differently than normal, because normally, like I just said, normally the theta M's or your muscle attachment angles are with respect to the limb itself. But in this case, because we're covering the distance, we're not really covering a limb in this case. We're basically just the distance between the outside of our thigh bone and our hip joint. So the only distance there is kind of just the femoral head. And so this angle right here is actually with respect to the horizontal. So this is a little bit different. So I do want to point that out, because normally when I give you theta M, it's with respect to a limb. It's just this, because the hip joint is a little bit unique in that, we don't have the full limb, an entire limb here that we're defining against. Normally it's more customary to define this with respect to the horizontal. And so what you'll see here then is the force summations are going to be a little bit more classical in the sense, but we only have one angle that we're working with. Okay. All right. And so the goal, as usual, is that we're going to solve for the amount of muscle force that we're exerting. Yep.
Why don't we consider the angle that the leg makes?
Yeah. And so we would do that if the theta M was defined with respect to that little segment right there. But because the only other forces we're considering here are just weight and normal force, those are just purely vertical. And then with the theta M defined with respect to the horizontal, that's the only one that we really need to sum the forces. Yeah. Normally you would need them though. Exactly.
That's why they did just.
Exactly. Yeah. Mhm. Yeah, there's a lot going on in this one in terms of, and even this figure is like kind of a little messy. This looks a little bit better than the one in the notes, actually, believe it or not. And so that's why I kind of chose for this one to give you just the angle straight up. But the next example that we're going to do is a bit more classical from what you're seeing in the homework. Okay, and so we're going to solve for the muscle force, and then we're going to solve for the joint reaction forces as well. Okay. Any questions on this? Okay. All right, and so let's go ahead and do our classic statics methodology. And so we're going to sum up all the forces in the x direction, sum up all the forces in the y, and then set it equal to 0. Right. So some of the forces in the x direction, we only have 2 in this case. So we have FM's cosine of 70 degrees. And what did I do? Okay, so JX is going in the negative direction. And so we have minus JX. Okay. That's equal to 0. So that's our first equation. 2 unknowns in that equation, so we can't solve it just yet, but we'll keep it in mind. Some of the forces in the y direction, we have FM sine of 70 plus JY, and then minus the 2 weights, or minus the weight of the leg, plus the normal force from the ground, which is 200 newtons. Okay. And that equals to 0. Then we have the sum of the moments around the joint. Okay. And so this is just like, just like all the homework problems, this is going to be the first equation that we can actually solve because it's only going to involve just one unknown. Okay. Here you have to be a little bit careful though, because because our muscle force here is kind of offset a little bit. And so we have both LM and HM. We have to consider both contributions, X and Y components of FM inside the moment equations. Okay. Okay. All right, so some of the moments around the joints. So let's do the vertical component first. Okay. And so we have FM, LM, okay. And this is going to be just the vertical components of the muscle force, right? Because remember, LM here is the horizontal distance, right? And so that's going to be the moment arm of the vertical component of the muscle force, right? And so that's going to be FM LM sine of 70. With the negative in front, sorry, because it's going to produce a clockwise moment. Okay. Then we're going to add FM HM. And so this is going to be the horizontal component of the muscle force. Okay, so this can be cosine 70. Okay. And it's a positive sign because that's going to produce a counterclockwise moment, right? And so if we kind of go around this way like this, then we know that that's counterclockwise. Okay. Plus the weight of the leg times the moment arm for the leg weight. And so this is going to be multiplied by LL. Okay. Plus the normal force from the ground multiplied by its moment arm. And so from the ground, we have 200 newtons. Okay. And that's going to be multiplied by LF, which is the moment arm for that force. And all of that's equal to 0. All right. And so this last equation right here only has one unknown, which is the FM, right? Remember, we sum the forces around the joint, and so that eliminates both of the joint forces from this equation. And so we can solve this one straight up for FM. Okay. And so FM in this case is 212.48 newtons. And so if you compare this muscle force to the very first example that we did at the hip joint, which was the first one that we did last Wednesday, let me go ahead and write the value just to kind of remind you. Okay. You can see that this muscle force is a lot smaller, right? And the only things that really changed between this example and the last one, so I ran, basically the same numbers for the weight and everything. And so the only thing that really changed was just the orientation of the leg itself. Okay? And so because we're standing on the cane, and of course, having the cane take off some of the weight, of course, that's going to help too. But the fact that your leg is in a much straighter position here, it's not as curved inwards, that places a lot less strain on your hip flexor muscles. Okay? And so that's why you see that the force here is reduced by quite a bit. And so just by using a cane, you can see that you kind of reduce the strain on the hip by about almost 4.5 times, right? But maybe about 4.25 times. Okay. All right. Any questions on this?
Would you also compare it if that orientation with full load of the weight of the body?
Mm-hmm.
Assuming that
Yeah. So I think probably if you want to do that, you would exactly right. Yeah, and so you can do this with 300 newtons too, and you'll still see you'll get a reduction for that. Yeah, I don't have the numbers for that in front of me, but you can kind of easily run that on. Yeah. Okay, so that's the muscle force, and so let's take that result and let's plug in and solve for the joint reaction forces, because we can plug in for here and here and solve for those ones. Okay. All right, so first we have Jx. Okay. So you can see here that Jx is equal to Fm cosine of 70. Okay. And so we just plug in our result for Fm, and what we get for Jx is 72.67 newtons. And Jy is going to be weight of the leg minus the 200 newtons minus Fm sine of 70. Okay. And you plug in for Fm, what you get is minus 300 newtons. Okay. And so you find the magnitude. Remember, these two are just components of a single joint reaction vector. Okay. And so you find the magnitude, so you take square root of Jx squared plus Jy squared. And what you get is 357.46 newtons. This is also a huge reduction from before. Because from the first example, let's see, from the first example, we got a joint reaction force of 1177.3 newtons. Okay. So you can see here that we've reduced the joint reaction force by quite a bit as well. And so, these two things are intertwined. And so, usually if your muscles are working a lot less, then that places a lot less strain on the joints. Okay. And this is true in general in most of the body, because if you look at the direction for the muscle force, right? Most muscle forces are going to take your limb and kind of at least partially pull that limb back towards the joint, right? And so you can see I think this was the shoulder joint here, right? And so as FM increases, you can see that it's part of that muscle force is going to be pulling the muscle back towards the joint this way, right? Same thing with this one right here, right? So as FM increases, it's going to pull the muscle along this, it's going to pull the leg along this line back towards the joint, okay? And so the more you can kind of reduce the amount of work muscles are doing, then it reduces that component of, the muscles pulling the limb into the joint. And so it's going to reduce the strain on the joint as well, okay? And so a lot of the, devices that are designed for like a mobility assistance or, for rehab, a lot of them are designed with the intent of, how can we reduce the strain on the muscle? So that's going to have kind of a ripple effect for a lot of the, a lot of good health benefits, not only for your muscles, of course, but for your joints. It's going to put less strain on your bones as well. Okay. Any questions on this? Okay, so that's the hip, and so let's do an example at the knee. All right, and so in particular, let's do an example where we consider a leg raise exercise. Okay. Okay. All right. And so, just like the hip, the knee is also one of the most major weight-bearing joints in the body. Okay. And it experiences a lot of compressive loads. And the knee is kind of interfacing with, I would say, two of the most powerful muscles in your body, which is your hamstring muscles in the back, and also your quadriceps muscles in the front. Okay? And so, just through the effect that we just finished talking about, how your muscles kind of place additional strain on your joints. Just from doing general walking or going upstairs, your knee can experience compressive forces that are about 3 or 4 times the amount as your body. And a lot of that is just purely due to the fact that, just by standing, just by walking, your thigh muscles are going to be tensing, and your lower leg muscles are going to be tensing as well. And so that places a lot of strain on your knee. All right, so let's look at the leg raise. And so for the leg raise, we have let's say that you're kind of just sitting down, and so your thighs are going to be horizontal to the ground. Okay. And so those are your thighs. Okay. And let's say that your lower leg looks like this, okay? And let's say that, at your ankles, this person is basically wearing a weighted ankle brace. And so it's going to apply some additional weight at the ankle. Okay? And so down here, we have the combined weight of the ankle brace and the foot. And let's say that weight is W. Okay. All right. So let me go ahead and draw the, basically a line that represents the lower leg. And so this line that I drew here represents kind of the long length of your lower leg bones. Okay. And so attaching onto your lower leg, you have your quadriceps muscle. Okay. And so let's say that we have a muscle force like that. Okay. And let's say that we have an angle here, theta m, okay? And this theta m is measured with respect to the leg itself. And then the lower leg with respect to the horizontal has some angle theta, okay? All right. And so in addition to the leg brace, we also have the weight of the lower leg itself. Okay, so let's say that we have a vertical force here. Okay, so we'll call this weight leg. And it's acting vertically downwards, just like that. Okay. All right. And so just like normally for these problems, we're interested in solving for the muscle force, as well as the reaction forces at the joints. And so we have a JX and a JY. Okay. All right. And so let's solve this problem just with symbols first, and then I have numbers at the end that we can plug in and actually compute stuff. Okay. All right. Any questions on this? Okay. Okay, so let me go ahead and draw just because the space is a little bit tight here. So let me go ahead and draw the free body diagram on the next page. Okay. So let's say that this is our leg. Okay. And so on the top side, we have the knee joint. On the bottom side, we have the ankle joint. Okay. We have the weight of the foot and the ankle brace at the end. And so that's going to be W. We have the weight of the leg itself, so we'll call this W leg. And then we have the muscle force acting this way, where the angle here is theta M. We know the angle here is theta. Okay. And so here's another trick that you guys can use to help you with the trigonometry, okay? And so one thing that you can do is you can basically draw a line that's perpendicular to the leg itself. Okay. And then the angle, because we're given angle theta right there, right? And so because we drew this line perpendicular to the leg itself, okay? That angle theta is going to correspond to this same angle right here. Okay. And so when you're computing things like for the moment, and we want to find out, the component of the weight forces that's going to contribute to the moment, we're going to use this that angle right there. Okay. And I didn't give you any lengths, so let me give you some lengths that we can use here. Okay. Let's say the distance between here and here, we'll call this LL, and that's measured along the length of the leg itself. Okay. And then the distance from the knee joint down to the ankles, we'll call that LW. Okay. And so when we're computing moments, we're going to use those two lengths. And then we're only going to use the component of the weight forces that are perpendicular to the leg itself. But again? LM. Yeah. Oh, LM, yes, we have that too. Thank you. Yeah, we definitely need that one. We can't solve it without it. Mm-hmm. Okay, so let's go ahead and sum up the forces. Okay. So some of the forces in the X direction, let me go ahead and draw on the joint reaction forces here. So we have JX and JY, okay? And so the some of the forces in the X direction, we only have two components. And so we only have JX, right? And then we have a minus FM cosine. And remember, because theta M here is measured with respect to the limb itself, and we can see here that this theta M is going in the same direction as this theta, right? And so if we kind of move theta FM down here, right? And say that this is theta M, right? You can see that the total horizontal component in this case is going to be theta plus theta M. Okay. And so that's the sum of the forces in the X direction. Next, let's sum the forces in the Y direction. So in the Y direction, we have JY. Then we have the y component of the muscle force. So this can be Fm sine of theta plus theta m. Okay, then we subtract out the two weights. So we subtract out the weight of the ankle brace, and we subtract out the weight of the leg. Okay, and that's all going to be equal to 0. And then finally, we have the sum of the moments around the joint. And so for this one, we have Fm. We only want the perpendicular component of Fm, right? We don't want the one that's parallel to the leg. So this can be Fm sine of only theta m in this case, because because remember we're doing moments here, okay? And then we multiply this by Lm. Then we have the perpendicular component of the leg weight, okay? And so basically we only want this component right here, right? Because that's perpendicular to the leg itself. And so that's gonna be WL or W leg times cosine of theta, right? Because theta is this angle right here, okay? Times the length, which is LL. And then we're gonna subtract out the moment contribution from the ankle weight. And so this can be minus W. Again, we have a cosine theta times LW. And all this is equal to 0. All right. And so those are all our 3 statics equations. And then we can solve them for our 3 unknowns. All right. Any questions on this?
Would have saved us a lot of homework. On the homework, I did components of each, like X and Y. Really good.
I see. Yeah, there's a lot of ways to do these, and there's just a lot of things to keep track of. So yeah, it definitely helps. It might seem like it's a lot of work just to kind of write out everything again, but I think it's important. It's really important to stay organized here. Yeah. Mm-hmm. Okay. And so just like we normally do, we're going to take the last equation and solve that one for Fm. Okay. And so if we do that, so I'm going to skip through the algebra just for the sake of time. Okay. Okay. And so if you solve algebraically for Fm from the moment equation, what you get is W leg times LL plus W LW times cosine of theta, right, divided by Lm sine theta m, okay? Let's put some typical numbers for these, just so that we can get a sense of how much this is. And so let's say that we have W leg is 50 newtons. Okay. W, let's say, is 150 newtons. Right? So he has a pretty heavy ankle brace on. Let's say theta m is 15 degrees. Theta is 45 degrees. Let's say that LM here is 12 centimeters. LL is 22 centimeters. And LW is 50 centimeters. Okay. And so we plug all that in, and we get Fm is equal to 1958 newtons. Okay. And so now that we have this muscle force, you can go ahead and plug it back into the force balance equation, solve for Jx and Jy.
that's pretty standard. And so I'll let you do that and confirm that. But what I want to talk about instead is, I want to dive a little bit into this guy, the insertion angle. Or the attachment angle. Right? And so remember, this is the angle that's at which the muscle attaches to the limb itself, right? And the fact that we have this this quantity here in the denominator with a sign term no less means that our value for FM is going to depend really strongly on the attachment angle. We talked about this a little bit with upper extremity, but I want to touch on it again here because it's important. And because there's something unique about the knee that where it affects this attachment angle actually quite a bit. Okay. Right. So remember what we talked about before with upper extremity, where generally the higher the value of the attachment angle, the less hard your muscle has to work in order to rotate your muscle. Okay. And the opposite is true as well. And so if your attachment angle is really small, especially when it approaches zero, then your muscle has to work really, really hard because there's just not really any component for that muscle in that rotary direction where it can actually rotate your limb. Okay. And so generally, what you want, at least in terms of ease for your muscles to act, is you want to have higher attachment angles. Okay? And so on the next page, I'm going to show basically a graph of how FM here varies with the attachment angle. Yeah. So bigger boy muscle, the better. Part of that is your muscle size, and so I think someone asked a question about that actually last time too. And so if you do have bigger muscles, it does kind of naturally pull up your attachment angle a little bit. But a lot of it's also just genetics, and a lot of it's just kind of how your body just kind of arranged itself in terms of what the attachment angle is. And you'll see, with the knee, there's something really unique where a lot of it is really genetics in terms of how hard your quadriceps have to work to extend your leg. Okay. Any questions on this? Okay. All right. So let me go ahead and draw a graph really quick. And so if we draw a graph of how the FM varies with theta, okay, it looks a little something like this. And so if you have a theta of 0, then which is not possible, but theoretically we can think about it. And so if your muscle made no angle of attachment, so it's basically parallel to your limb, then there's nothing the muscle could do to ever rotate your limb. It would just always just pull the limb back into the joint. And so that's why here you can see that on the y-axis it's kind of unbounded. Right, because we have it's basically infinity, but that's not possible. And so most of the time you don't have any attachment angles that are 0. Okay, but you can see as the attachment angle gets higher, then the muscle has to work less and less hard. Okay? All right. Okay. And so the knee actually has a very unique way to increase the attachment angle strictly of the quadriceps muscle. Okay. And that unique feature is the patella. That little the little kneecap of your knee, right? And so if you draw kind of a cross section of your knee joint, okay? Basically you have down here, which is your lower leg. Okay? Your patella is kind of like this little, you know, almost like a pebble shaped bone, which attaches right here. And then your quadriceps actually go on top of the patella. And so they kind of stretch over the top. Okay. So this is an exaggeration. So it's not actually this thick around. Okay. But the quadriceps, you know, kind of has to go around your patella. Okay. And so you can see, you know, because the quadriceps have to go around this, like it's literally like kind of almost like a pebble in a stream. Right? Because it has to go around that thing, your muscle force attachment angle is going to be naturally higher. Just because, you know, the attachment point for the quadriceps on your lower leg is actually just distal to the patella. Okay? And so because that patella is there, it kind of forces the quadriceps to kind of bunch up a little bit, and that increases the attachment angle. Okay? Okay. All right, question. So then a bigger patella surface area will increase the angle of attachment. Yep, that's correct. Yep. And so if you just happen to be born with a bigger patella as someone else, then your quadriceps actually have a higher mechanical advantage compared to people with a smaller patella, or even people who have to have their patella removed for whatever reason. Maybe they hurt it really bad and they had to get it removed. Then that person's quadriceps have to work a lot harder than normal because they don't have that little, you know, pebble or that little speed bump that increases that angle of attachment. Okay? But for most people, this is just strictly genetics, and so how big your patella is kind of, you know, there's not much you can really do to increase the size of it after you're born, and so you know, just naturally, just some people are going to have a higher mechanical advantage compared to other people. Okay, and it's strictly just a mechanical advantage, you know, thing, right? And so it has nothing to do with how powerful their quadriceps muscle are. It's just some just attach at a much better angle than others. Okay. All right. Any questions on this? Okay. All right. And so that's the knee joint. And so I did want to do one example with the ankle before we close up here for lower extremity biomechanics. Okay. So let's go ahead and do that. Okay. All right, so the ankle joint is actually pretty unique in that it's an articulation of 3 different bones. Right? Okay. And so the 3 bones are your two shin bones, so the fibula and the tibia. Okay. And so both of your shin bones actually come and attach at your ankle to some degree. Okay. And then the 3rd bone, of course, is your foot bone, which is the talus. Talus specifically being your heel bone. Okay. And so primarily your ankle joint is a hinge joint, but it does allow some other motions as well. But mostly it's considered mostly a hinge. Okay. And the two main actions that the ankle can do are plantar flexion and dorsiflexion. Okay. And remember, the main muscle that's responsible for plantar flexion is your calf muscle. Okay. And dorsiflexion, remember, that's when you try to point your toes to the sky. And so this is an action for the muscle in the front of your leg. And so it's not talked about that much because you don't do dorsiflexion all that much compared to plantar flexion. The water fountain outside is getting a root canal, sounds like. But the muscle that does dorsiflexion here is called the tibialis anterior muscle. Okay. And so it's possible to, that you have a lateral and medial version of the knee of the ankle, sorry. But these are the two main actions. And of these two, the one that's by far a lot more important, especially for regular walking or jumping, is the action of your calf muscle. Okay. And so this example here is we're going to basically examine how the calf muscle acts on a foot that's plantar flexed. Okay. All right, so this example is a foot that's standing on its toes. Okay. And so here is our foot. Here we have the muscle force. Right, just like before, because the ankle here isn't a straight up limb, I'm going to define the attachment angle with respect to the vertical this time actually. And so theta m here is with respect to a vertical line. Okay, it's going to look like that. The ankle joint itself is actually kind of in the middle here. Okay, and so your calf kind of attaches on the back of your heel, whereas the centroid of the ankle joint is kind of in the middle part of your ankle. Right? And so we have the ankle joint here. And just for simplicity's sake, we're going to assume it's on the same horizontal line as the calf muscle. Okay. Okay, so we have JY, JX. Okay. The length from here to here is LM. And the other force that we're going to be applying here is a weight force, which is going to be applied as a normal force from the ground. Okay. And this distance right here will be L. Okay. All right. And so let me give you the numbers for this. So let's say that LW is 5 centimeters. W right here is 300 newtons. Okay. And the insertion angle that we have here with respect to a vertical line, let's say this is 30 degrees. Okay.
Vertical line is what we assume is the muscle that's connected to the bone.
Yeah. Yeah. Mm-hmm. And then LM, I think it's probably on the next page. Oh, I didn't write down LM. But LM, I did have it. Oh, right here, LM is 3 centimeters. Let me put all my parameters in the right place. Okay, and so fairly simple example here. So there's not too much going on. So it's kind of a pretty standard statics problem. But just like we've done before, we're going to solve for the muscle force and each of the joint reaction forces. Okay. Calf raises, yes. Yeah, your calves are a really important muscle, so make sure you're taking care of them. Yep. Mhm. All right. Any questions on this? Okay. All right. So let's go ahead and just run through this really quickly. So this one's pretty quick because it's everything kind of aligns pretty well. All right. So we're going to start with some of the moments around the joint. Okay. And so we're going to do WLW minus FM. And in this case, because the angle is measured with respect to the vertical, we're going to take the cosine of that angle. Okay. LM. And so that's going to equal 0. And so we can solve this simply for FM. So that FM is equal to WLW divided by LM cosine theta M. And so we solve for this, we get FM is equal to 577.35 newtons. Okay. All right. And so just like we've seen in all our examples here, you can see the muscle force is much higher than the force of the external load. Okay. And that's only just because of the attachment. All right, and then finally, we can solve for the joint reaction forces. And so if we plug into our joint reactions, we get Jx is equal to minus Fm sine theta. Okay. And so this is equal to 288 minus 288.68 newtons. Okay. And then Jy in this case is equal to minus Fm cosine theta plus W. Okay. And so this is equal to minus 800 newtons. Okay. So you can see most of the joint reaction forces are in the vertical direction because that's the direction the weight is acting. And our muscle force here has a much higher vertical component than horizontal. Okay. All right, any questions on this example? Yes, there is an M on the theta. Thank you. Yep. Yeah, there's only one theta here, so it should be theta. Okay. And so that's it for the static analysis of the lower extremities. Before we move on to spinal biomechanics, I did want to talk about some common injuries that you can sustain in the lower extremity. Okay, and so I think that'll be kind of the last thing that we talk about today. And then on Wednesday, we'll start up with spinal biomechanics. So let me stop sharing here. Okay, let me share my screen here. Okay. All right, so let's talk about some common injuries that you can sustain here at in the lower extremity. Okay, so let's start with the hip. And so, like we said before, the hip is a pretty stable joint, and so the socket of the femur fits really well into the pelvis bone, right? So their dislocations are pretty rare, but you can sustain some other injuries here. Okay, so one of the more common ones is a fracture. Okay. And so one of the more common places to get a fracture is at the femoral neck, which is what you can see in this image here on the right. Okay. And this is especially common for elderly individuals with osteoporosis. And so remember, osteoporosis is a disease where your bones get less strong. And so it makes it so that, this part right here, which is actually subject to a lot of shearing forces compared to other parts in your body, right? Because you can imagine as the hips are kind of loaded from below, right? Then this is going to cause some shear to happen in kind of this plane right here, okay? And so for individuals where their bones are less strong than normal, then this is going to cause some fractures in this region because, as we know, that bones are not as strong in shear as they are in compression or tension. Okay. Yep.
How would you heal a break like that? Would you do a full leg cast? Like, how would you make sure, like, how could you stick the leg together?
Yeah.
Like, if you had a complete break off.
Yeah. So probably if it was a complete break off where, the bone actually becomes detached, I would think you would, yeah. And so you would definitely need surgery at the very least. And you definitely need to immobilize the leg as it heals. And so you probably need a full leg brace, definitely be in a wheelchair for, for a long period of time, maybe permanently if the patient is old enough. But if it's if it's only a partial break and maybe it's a microfracture, you can probably, try to just, immobilize that, definitely limit the amount of weight bearing that you do, maybe like take a crutch or something like that. But, of course, it depends on the severity and how old the patient is. All right, so the next type of injury is contusions. Okay, so contusions are just bruises. And so I think everyone's received like a dead leg before, right? And so people just kind of like punch the front side of your thigh. And so that hurts like hell. And so that's a pretty common injury just because like if you play soccer or anything like that, where people are kind of running into you and they knee you in the thigh. So, it's kind of a very wide target for a lot of blows to happen. And so contusions are also very common for the hip as well. Okay. And hamstring strength, right? And so I think everyone's probably familiar with the term "I pull the hammy," and so that refers to pulling your hamstring. Okay, and so that happens a lot because it's just because the muscle is just so big. Okay, and kind of the situation where you can pull the hamstring the most is if you have hip flexion. So remember, hip flexion is when you kind of bring your entire leg up like this, and you have knee extension. So you kind of put the hamstring in a state where it's like extremely stretched, right? And the hamstring usually doesn't like to be like that because, if you think about your normal everyday walking, that doesn't happen all too much. Where you have both your hip flexed and your knee extended. And so if you ever find yourself in a situation like that, then probably you're going to be in danger of pulling your hamstring. Right? So most of the time this happens during athletic activities, just because during routine, just walking, you don't do both at the same time. Just be aware that it is a concern unless you are pretty flexible. Okay, so those are common injuries at the hip. So let's talk about the knee and the lower leg, because these ones are actually really common. Okay, and so what you can see right here is a common situation in football, right? And so a lot of times when football players get tackled, they get tackled from their lower legs, just because it's kind of an easier tackle to make. But it's actually, from a biomechanics standpoint, something like this is actually really scary because you can kind of very easily injure your knee. And so let's go through all the different kinds of or the most common knee injuries that you can have, and let's talk a little bit about how they can happen. Right? And so probably one of the more devastating knee injuries you can have is an ACL tear, okay, or an ACL injury. And so remember, your ACL stands for the anterior cruciate ligament. And so that's the main ligament inside your knee that kind of prevents your knee from kind of sliding up and back. And it also provides some stability and twisting as well, although it's not so strong in that. Okay. And so these are very common in sports, which require a lot of pivoting and cutting. Right? And so anytime you basically drive your foot into the ground and put all your weight on that foot, kind of in a very exaggerated way, and try to change directions rapidly, that puts a lot of strain on your ligaments in your knee. And so those are probably the most common instances where you can tear your ACL. Okay. And in fact, most of the ACL injuries are non-contact. So what that means is that, you actually don't have another player or another force that's actually impacting you from the outside. It's strictly just from your own action. Right? And so you can see here that, it happens most common when their foot is planted, and the femur is greatly rotated. Okay. All right. Next is the PCL injury. So the PCL is the other cruciate ligament on the inside of your knee. So that's the one that forms the cross. Okay. And so these are not as common, but they can happen. Okay. And so these typically occur when the knee is hyperextended and the foot is plantar flexed. And so remember, your plantar flexion is you're pointing your toes downwards, and hyperextension of the knee means you make your knee kind of extend past its range of motion. And so this would probably have to be some kind of unnatural action too. Yeah.
For this one, are you saying that, like,
if this is your knee, like it's bending all the way, like.
Other way.
backwards Like this?
Other way. So it'd be extended, extended upwards like this. And so
Oh, you're saying it's coming like this?
exactly.
Oh,
So it would have to extend kind of past, because normally it only extends so far that it makes kind of a straight line.
oh,
So hyperextension would be if you extend past that. And then your foot is also kind of plantar flex at the same time.
okay, so basically your knee is then coming past
Exactly.
90
Yeah.
degrees.
Yeah. Mhm. Let's see. Yes, yeah, it could happen that way too. Yeah. Anytime you kind of like fall and you kind of brace your leg with your leg kind of gets caught in something and kind of, and you kind of get stretched like that. That's how I kind of see that happening. But at least personally, I've met people, a lot of people that have had, knee injuries, but I haven't actually personally met anyone that's had a PCL injury before. But but they definitely happen. It's just that they're just not as common as the other ones.
Like, what is it, like, fell off and oh, like if you fell off the chair.
Yeah.
into the ground?
Yeah. Mhm. Actually, if you follow basketball, the MVP of the finals last year, Giannis, he had a hyperextended knee. And I remember one of the concerns they had was that he hurt his PCL because he kind of grabbed a rebound, he kind of came down awkwardly and kind of extended his knee a little bit too much. Yeah. All right. So the third type of injury is an MCL injury. And so remember, the MCL is a ligament that actually goes over the outside of your knee. And so the M in MCL stands for medial. And so that means it's on kind of the inner side of your knee. Okay. So this one's really common. And actually, the image that I'm showing you here, probably my main concern would be for an MCL injury. Okay. And that basically, and remember your MCL and your LCL, they kind of prevent your knee from bending, inwards and outwards. Okay. And so MCL injury happens when your leg is, when your knee is kind of bent inwards. So it's bent back towards the middle of your body. Okay. And so any kind of blow that's going to hit your knee from the outside, either on the left or the right, depending on what knee that you're doing, that's going to sustain some risk for MCL injury. Okay. And so these MCL injuries, these are typically a contact type of injury because it's usually someone has to hit you from the outside with a large force in order to stretch your MCL. Okay. All right, and the fourth type of injury is an injury to your meniscus. Okay. So remember, we talked about the meniscus is kind of like this little soft pad of soft tissue that's on the top of your tibia, okay? And it kind of helps with shock absorption. And so what can happen sometimes is because your MCL actually attaches straight to the meniscus, and so any kind of stretching to the MCL could actually injure the meniscus as well, okay? Because it's actually not as strong of an attachment compared to a bone attachment or tendon attachment. And so when you stretch the MCL, it can actually, kind of tear off or compromise the meniscus along with it, because the meniscus is just a lot softer than your tendon and your bones. Okay. And so if you have a torn meniscus, it can kind of do this thing where it kind of flaps, and so it's like kind of a partial tear, and it kind of just kind of sits there and kind of flaps like this. Okay. And that flap actually interferes with some normal joint mechanics. And so I actually tore my meniscus when I was in high school playing soccer, and it's definitely not fun because you can definitely feel when it flaps because like your knee kind of like buckles a little bit and you kind of feel like it pop a little bit, and it's not pleasant because it kind of happens randomly and it's hard to kind of predict, and just all of a sudden you might hear like and you kind of jump forward a little bit. So yeah, it's not fun. I had to get mine kind of like surgically removed just because there was kind of no way for them to kind of put it back to where it was. All right. Any questions on this? Do I still have PTSD? No, it was kind of a weird thing because I got it when I was kicking a soccer ball. So no one hit me or anything like that. I just felt a pop in my knee when I kicked it, and then it was yeah, I got it checked out, and it was a meniscus. I mean, thankfully it was just the meniscus. It wasn't my ACL or anything like that. So yeah, it wasn't, definitely not as bad as it could have been. Okay. Okay. And so this is lower leg injuries part 2 because it's a part of the body that gets injured a lot, right? And so another type of injury that can occur are overuse injuries, right? And so these are things like stress fractures, okay? But for the knee, because the main supporting structures in your knee are actually the ligaments, what you can do is you can kind of overuse those ligaments, and they become weaker and they become more susceptible to injury, okay? And so one particular type of overuse injury, which is uncommon for swimmers, is breaststrokers knee. Okay. And so if you're familiar with kind of with the breaststroke motion, you kind of like kick your legs back and you kind of bring them together really suddenly. And that motion of actually bringing your legs back together, you can kind of see that it kind of puts your knee into this kind of inward bending motion, which is not good for the MCL. And so while not nearly as traumatic as like a 300-pound football player hitting from the outside, like if you do the breaststroke, continuously over and over and over again, eventually all that wear is going to get transferred to the MCL, and you're going to have some fatigue type injuries. And so breaststrokers are actually another category of people that injure their MCL, but it's not through any kind of traumatic injury. It's just because of the motion of the breaststroke just puts so much strain on this inner knee right here. Yeah, so both of their knees. Okay? And it's mostly just because they're kind of kicking their legs out and kind of bringing them back in suddenly. And so that kind of weird motion kind of puts just a lot of strain on the MCL. Okay. And so another type of overuse injury you might have heard of is called shin splints. Okay. And so this is a lower leg injury. Okay. And so this is an overuse injury with respect to the tibia muscle, so the muscle that attaches kind of on the front of the leg. Okay. All right, and the last injury that we'll go over for the lower leg is a patellofemoral pain syndrome. Okay, and so this is characterized by any kind of motion of your patella is going to cause you pain, right? And so the cause for this is still unknown, but hypothesis out there is because of just some kind of anatomical misalignment. So, maybe you were born where your patella doesn't fit as correctly on your knee as other people. And so this misalignment can cause some strain on, maybe the ligaments and the tendons in your knee. And that's going to cause you some pain. Okay. All right. Any questions on this? Okay. Let's see. We have 1 minute left. Okay, and so I think this is the last one, right? Yeah, okay, it's the last one. Oops. All right, so very quickly, so injuries for your ankle. So an ankle is another part of the body which is injured a lot. Okay, and so probably the most common are ankle sprains. Okay, and so if you played any kind of sport, you probably sprain your ankle. Okay, and so an ankle sprain involves some kind of injury to the ligaments in your ankle. And so probably the most common ankle sprain out there are sprains on the inner ankle. So those are medial ankle sprains. Your lateral ankle sprains are a lot more common, okay? Because your ankles tend to roll inward. Okay? And that's because the ligaments and the tendons on the outside of your ankle are just naturally a lot more weak than the ones on the inside. Okay. And so that's why you end up with lateral ankle sprains a lot. All right, another type is overuse injuries. And so one particular overuse injury that's being studied a lot is your Achilles, okay? And so your Achilles tendon is the tendon that attaches your calf muscle to your heel. And so, in some people, and mostly athletes, they use this so much that the Achilles tendon can just rupture. And so it's still, this is still a very kind of hot issue of research because, people haven't been able to find kind of a good cause for it. But it's very catastrophic when it does happen. Okay. And the last type is alignment anomalies, right? And so just like with the knee, if your ankle bones don't fit together really well, this can cause a lot of pain and a lot of strain on your ligaments and tendons as well. Okay. All right. So any final questions on this before we wrap up lower extremity biomechanics? Okay. All right, so we're out of time, and so I'll leave it here. And then on Wednesday, when we come back, we'll start spinal biomechanics, which is the last part of our static analysis. And so, hope everyone has a good afternoon. Hope you guys enjoy the class today, and I'll see you on Wednesday. Thank you too. Sure.
When it comes, it's not, it's somewhat related to today's lecture, but somewhat not. So how do your tendons and ligaments gain strength relative to your muscles, right? You don't get a large amount of blood flow. So do they ever add new tissue at any point over time from like hypertrophy effect, or do they just never get any larger weight?
They do. I mean, it is possible for them to heal. I mean, people who injure their ligaments can heal them eventually, but it's a very, very slow process. And so, for all practical purposes, you can assume that your ligaments and tendons just kind of stay the same. And so, unless there's some kind of injury, then they're not going to be doing much growth.
Okay. Yeah, because this weekend there was a powerlifting meet and like something similar happened. Let me see, 2014 maybe. And basically one of the lifters this weekend had like a catastrophic accident where he was squatting like really heavy, like 750 maybe 743, and basically he was just like going on the way down and all the ligaments in one of his knees just completely snapped.
Oh man.
And then like now he's on one leg. I haven't watched the video yet just because I find that stuff kind of disgusting, like especially since I let's face myself down. So I'm just like, I mean, not nearly that heavy, but an accident can happen anytime.
Yeah.
And this guy's huge too. He's like over 300 pounds. So
Oh man.
basically, because of the way that it happened the first time, is like in most powerlifting federations, you don't lift with safety straps. You lift with spotters. But like when 743 pounds, like all of a sudden it's just not being supported by anything anymore. It's like catching that is extremely difficult, even with like 6 people.
Oh
So
yeah.
I'm guessing what happened in this case, just like the last time, is like all the ligaments gave out, and then that 700 pounds just crushes you basically.
Oh man.
So it blew out all the ligaments in his other knee too.
Oh man.
And now he has to go get surgery and stuff tomorrow.
Oh man.
But I was just wondering about that because he was like really up and coming, like he was going to be, looking like he was going to break some world records and stuff. But the thing is, he gained so much strength so quickly. So I was wondering how that process worked, where like, did his ligaments ever get any bigger at any point, or his tendons, or are they just that way permanently? And so he just kind of has to, like, I guess, just get more muscular in order to support that type of weight, like or either that or make some flexibility adjustments or something.
Yeah, it's a good question. I have heard of that, where if you gain strength too quickly, then I think it puts your ligaments in danger and your tendons. I think what's happening there is that your ligaments and tendons actually get more flexible. I mean, so as you're kind of gaining more muscle strength and you're kind of putting more strain on that, they actually kind of almost sprain them. You kind of stretch them beyond their capabilities.
Okay.
And then they kind of just kind of get looser in that respect, where they kind of get fatigued in a sense, kind of like material fatigue, and they kind of stretch out kind of a little bit. Whereas I think, like you said, he probably gained strength too quickly. But this might have still been a little bit stiff, and so he put just so much weight on it at one time that it didn't have the flexibility in order to sustain that.
So he put it under like basically such a large compressive load while it was already irritated from being stretched so much.
Yeah.
And then that basically caused failure.
Yeah, that's what I would think. But yeah, it's scary. I can't watch those videos.
No, yeah, it just grosses me out. Like some of them are just like so like it's just like I saw one the other day that like I wasn't expecting because like it just came up on Instagram. And usually those ones just say like sensitive content warning, but it didn't say anything. And it was just so gross because I don't know if you've ever heard of a pendulum squat. So like, it's like a squat that's like, you put your pads, you put your shoulders on the pad, right? And then like, it comes down into almost like I think the motion is more like a pendulum, which is why they call it that. You're moving in like this, you're squatting in this type of motion, right? But in this one, the pad, the weight was behind him instead of it being in front of him like it normally is. And so he was a little bit short for the re-rack. So he did a calf raise, and you're never supposed to do this on leg machines where you fully lock your knees out.
Oh yeah.
So because like with the leg press, the hack squat, like that puts you in major danger zone. Knee injury. So oh God, it was so dumb. He did like a calf raise, and then like one leg came off the pad
Oh.
and this leg fully extended and then
Oh.
he just fully collapsed all the way
Oh my
backwards.
God.
And it was crazy because it collapsed backwards and it caused him to start falling. And then he rolled from underneath the pads and like completely fell off the machine.
Oh,
And I
man.
was like, damn, I did not want to see that. Like, please put a sensitive content.
Oh, man. Oh, I'm getting, oh, my stomach's turning just
I
thinking
know,
about that.
it's just, it's gross. Sure. All righty, Professor, I'll see you in a couple.
All right, I'll see. Can you take the trash can off that one?
Yeah. I got it.
Thanks.